In this video, you are going to learn how to use the PETSc for Python interface to solve a simple linear sparse system of equations iteratively that describes the heat equation in a one-dimensional rod. You can then run the file in order to visualize the curves of temperature on the rod over time. Let's get started. Hi and welcome to this new video. Today I want to introduce PETSc to you in its PETSc for Python interface. PETSc is a software toolkit for solving large sparse linear systems, but also has options to solve nonlinear systems and ODEs, which you commonly find if you discretize partial differential equations in scientific computing or simulations in general. PETSc is an abbreviation and stands for Portable Extensible Toolkit for Scientific Computing. PETSc is a huge library offering a lot of fine-grained detail or fine-grained control on the involved solvers. But today we want to look at just a super simplistic example to make you aware of how PETSc works. And this example will be the transient 1D heat conduction example. And for simplicity, we will be using Dirichlet boundary conditions here. In this example, we also will not make usage of the parallel capabilities of PETSc. That is because once you want to solve partial differential equations with really fine discretization, you have to make use of large computers, which PETSc can do with the MPI interface, but we won't be using that today. Let us first look a bit at the mathematics behind. U describes the temperature in a one-dimensional rod. And the equation for heat diffusion is given as the temporal derivative of the temperature equals the second spatial derivative. And for simplicity, I left out any constitutive material parameters here. Then, as said, we will have Dirichlet boundary conditions, and the most simple case, we have homogeneous Dirichlet boundary conditions. That means that at every point in time, our solution will be zero at the two boundaries of the domain, so at the left end and at the right end. Then we want to start our time stepping with an initial condition that is this kind of step profile. So our domain goes from 0 to 1, and at a certain interval in the domain, our solution is 1. So think, for instance, of 1 degree Celsius, and at the rest of the domain, it is going to be 0 degrees Celsius, including the boundary conditions. And then we will expect that this profile will smear out over time, and this is what you've already seen in the intro. What is our solution strategy here? We are using an backward in time, central in space, finite difference approximation, and I want to introduce that to you. For this, consider U hat to be the solution at the next point in time, so when we increase our time by a time step delta t. And then we can approximate the derivatives in our partial differential equations with this backward Euler step here by saying the temperature at the next point in time minus the temperature at the current point in time divided by the time step length. And then for the spatial derivative, we will use a central difference approximation, which reads in this way, where we move one index element in our mesh to the left and to the right, and then we subtract 2 times the element in the center and divide by the element length or the discretization length squared. And since we are using an implicit scheme, that means that the time points for the spatial derivative approximation are sampled at the future time point, so U hat, and not at the previous time point, which would bring us an explicit scheme. And then we are imposing the boundary conditions by saying that the value at the next point in time at the very left of our domain, so the 0th index in our mesh, shall be 0, and the value at the very right of the domain, so with this -1, the Python syntax, the last element in our mesh is going to be 0 as well. Then let's make some rearrangements. First multiply by delta t, and then bring everything that does not have a hat on the right hand side and everything with a hat on the left hand side. And then we get the following equation here. So we have the ui from the previous time point on the right hand side, and on the left hand side we have the u hat and then plus, and now take care that here the signs have changed. Now the element in the center has a plus in front and the two off elements have a minus. And the cool thing about this is that we can express this update rule as a system of equations. That's because if we want to update the u hat at point I, we also need the information from u hat at point I minus 1 and point I plus 1. So we can write this as the classical form of a linear system of equations with a system matrix A, an unknown vector x, and the right-hand side B. And this system matrix then looks as following, that we have some sort of like a tridiagonal structure, almost. And on the main diagonal, we will see this 1 plus 2 times delta t divided by delta x squared. That is exactly what you would be getting if you take the u hat at I elements by having here 1 plus and then this times 2. And then on the diagonals next to it, we get the minus delta t divided by delta x squared, which arises from these off elements. And then I said almost tridiagonal. That is because for simplicity, we will not eliminate the Dirichlet decrease of freedom. So we will keep a 1 at the top left and the bottom right to indicate that the unknown in our unknowns vector x, which is associated with the boundary value on the left and on the right, is prescribed. And then we get the following sparsity structure, which is going to look as here. And there it should also be visible that this is not a tridiagonal system. What you commonly see is that people eliminate the Dirichlet degree of freedom, and then you will get a matrix that looks like this, which will then be tridiagonal and symmetric. But let's just leave that out for simplicity. That is because PETSc can of course also handle non-symmetric matrices. Then let's start with the implementation. For this, let me go down here and first import the very main package, which is going to be PETSc for Pi. Then we also need the sys package. I will show you shortly. We need numpy, s, and p for the preparation of the right-hand side. And I will also use matplotlib.pyplot as p.t in order to visualize our results. And then we have to initialize PETSc for Pi by saying PETSc for Pi.init and pass over sys.argv. Sys.argv is the list of arguments our Python file is executed with. And this has to be handed over because that is a common pattern when you see MPI-based programs. Although we will not be using MPI here, we still make usage of these arguments when we then later on execute our file. And then once PETSc is initialized, we can import the actual PETSc package by saying from PETSc for Pi import PETSc. Then let's define some constants. So I want to use 128 discretization points here. And for the temporal discretization, I want to use a time step length of 0.005. And I want to perform 10 time steps. So n time steps will be 10. Then let's create a main function and leave it empty for a second. And then call the main switch. So if name equals main, then execute the main function, which is necessary that our function is only executed with the Python interpreter. Then we can infer the element length or the dx from our number of element points. So element length will be 1.0, which is our domain length, divided by the number of finite cells, finite elements, and they are given as n points minus 1, since we are using a uniform Cartesian grid. And then let's build up that mesh by saying mesh is np.linspace, linearly spaced from 0 to 1, with our endpoints including the very left and the very right point, which are our boundary nodes. And then we can already start with creating the PETSc objects. And we need to create a matrix for our system. Then we need to create a right-hand side and then also allocate a vector for our solution. But let's start with the PETSc matrix. So for this, we will create a new sparse, PETSc matrix, fill it, and then assemble it. We can create a matrix. I want to call this A here for our system matrix by saying PETSc.met for matrix dot create aij. And aij is PETSc's way of storing compressed sparse row matrices, which are common in those sparse linear algebra terms. And we have to give it the dimension of this matrix. And we have a square matrix, which is endpoints by endpoints, since we include the two boundary nodes in our system and our degrees of freedom. And let me also show you why we need a sparse matrix here. That is, of course, because we only have a couple of non-zero entries, and all the elements that you find in the top right and the bottom left of our matrix will be 0. And once we reach really large domains, let's say 1,000 points, 10,000 points, it would be unreasonable to store these matrices as dense arrays. Anyways, let's continue and say a.setup. This will allocate all the necessary arrays by PETSc, and then we can prepare the assembly of our matrix. For this, let us pre-compute the diagonal entry of the matrix, which shall be 1.0 plus 2 times the time step length divided by the element length squared. And just to remind you, that is going to be this element here. Then we can similarly pre-compute these off-diagonal entries. So let's say off-diagonal entry. And this one is minus 1 times the time step length divided by the element length squared. Then before we assemble the actional tri-diagonal part of the matrix, let's fix the ones on the top left and bottom right of the matrix by saying a.setValue. And then we have to use indices similar to how you would index NumPy arrays. So let's say 0, 0, 0th row, 0th column, say 1.0. And here we have to be a bit careful. We can't use these bracket indices that you might know from NumPy. In some situations you could do that, but here we will resort to this setValue method. Okay, let's similarly set the value at the bottom left by saying at entry endpoints -1, endpoints -1, and 1.0. And just to remind you, PETSc follows the Python paradigm, or more precisely the C++ paradigm, that you start indexing at 0 and you exclude the very last point. So the last element will be at endpoints -1 instead of endpoints, though we still have an endpoints by endpoints matrix. Okay, then let's, for simplicity, just use a loop in order to fill up the tri-diagonal parts by saying for I in range of 1 to endpoints -1. And here remind yourself that the range command is similarly also exclusive the last element. So imagine endpoints would be 5, then we have the range from 1 to 4. This would then be the elements 1 to 3 and not 4, so that we don't overwrite the very last point. And then we can say a.setValue at I, I is going to be the diagonal value, the diagonal entry. So basically, when you look at the matrix here, you see that is at 0.11, at 0.22, 0.33, and so on and so forth. And then this one here would be at 0.10, and this one would be at 0.12. So it is in the same row, but is offset one to the left and one to the right in the columns. So let's do that and say a.setValue at I and I -1 is going to be the off-diagonal entry, and a.setValue at I and I +1 is also going to be the off-diagonal entry. And now our assembly or our pre-assembly is finished, and we can call a.assembly, which basically says PETSc that it can then write all the buffers it has created. And this is especially necessary if you have distributed memory systems where all the memory has to be moved to the parallel machines. Here in our case, it's just necessary in order to follow the convention. Okay, that's our system matrix. Then let's define the initial condition. And here I wanted to use this step profile that you can find here. So let me define that using an numpy where command. So I say my initial condition, so basically the temperature profile at the start, is numpy.where, and then we need a condition, and I want to have it at mesh points that have coordinate values of greater 0.3, and they shall be having values smaller 0.5, and then I want to use 1 and otherwise 0. That means our initial profile is 1 if the coordinate of the mesh vertex is between 0.3 and 0.5, and it is 0 otherwise. Then we can use that in order to assemble the initial right-hand side to the linear system. And for convention, I will also just call that B here and say this is going to be a PETSc.vector.create sequential and put in the endpoints. And then we can just say b.set array in order to set the entire vector array at the same time and fill it with the initial condition. And that also works because both have the same shape. And in this particular case, we would already ensure that our Dirichlet boundary condition is 0, since the initial condition is also 0. But here I want to explicitly do that in order to highlight it by saying b.setValue at point 0 is 0. And here, of course, we only need one index because we are just accessing a vector and not a matrix. And then b.setValue at endpoints -1. So at the very end of our domain, the right boundary point is also going to be 0. Then we have our right-hand side assembled, and last step is to allocate a PETSc vector storing the solution to the linear system. And this one I want to call it X, also in convention, which will be PETSc.vector.create sequential and hand over endpoints. And then last step before we can start our time stepping is to instantiate a linear solver. So we will instantiate a linear solver, and in our case this will be a Krylow-Subspace linear iterative solver. And I want to call this KSP. This is for Krylow-Subspace problem, I assume. And this one is given as PETSc.ksp.create. And Krylow-Subspace is just a mathematical term for a collection of a lot of linear solvers that share some common properties. And here we will mostly resort to the GMRES algorithm, which is a linear iterative solver that can handle non-symmetric systems that we have here. Of course, if you were to eliminate the Dirichlet boundary conditions and have a symmetric matrix, you could, for instance, also access the very fast conjugate gradient, but I will leave this to you as an exercise. The KSP requires us to set a system matrix, of course, because a linear system is associated with its system matrix, by saying KSP.set operators and then feed over the system matrix A. And then I will just use KSP.set from options. And this will basically read these command line arguments that we initialize the PETSc library with and uses them in order to select the linear solver and some other options like the tolerance and stuff. And just for a simple printout, I want to see what kind of solver PETSc has chosen for us and say chosen solver is ksp.getType, and then just print that out by saying solving with and then the chosen solver, and I'm using a format string here. Then let's start our time loop by saying for iteration in range of n time steps. And of course, the main step in every time loop is to solve the linear system of equations by saying ksp.solve b, x. So solve the linear system that is associated with system matrix A with the right-hand side B and store the solution in the PETSc vector X. And then we have to reassemble our right-hand side based on the updated information from the solution by saying here reassemble the right-hand side to move forward in time. And for this, I want to extract the current solution, which is x.getArray. Similar to setArray, we can also get the information from our PETSc array or vector, and this will then return a NumPy array, which we can use to do NumPy operations and then also visualize it. But here I want to use that in order to update our right-hand side by saying b.setArray current solution. So we will overwrite the right-hand side. And then, similar to before, I want to explicitly set the boundary conditions. So b.set value at 0 is 0, and b.set value at n points minus 1 is also 0. And that should already be it. That should be solving our linear system of equations. But I also want to visualize that. So let's do some visualize and do plt.plot on the mesh and the current solution, and then plt.draw to interactively update that, and just an artificial pausing here because our system is solved really fast. It is a super simple linear PDE and the solver is quite advanced here. So let's just introduce this artificial pausing such that we can see our solution. And before the time loop starts, I also want to plot the initial condition in the same figure, such that we also see our profile there. And in case we haven't made any errors, we should be able to execute that by running Python and then the name of the file, PETSc Python here. And of course, I made an error. Let's see. Okay, it should of course be assemble, not assembly. Let me check. And here you go, that's the solution you've seen in the intro. So basically what we see is that, oh well, maybe we should add an plt.show in the very end in order that our file keeps running. And then let's re-execute. And basically you see in different colors the values at different time steps. So we start off with this step profile, and then we slowly decrease in amplitude and as well as in shape of the solution. And that is what I mean by the solution gets smeared out. And also if you think of a temperature distribution in this rod, and for instance you say you have some ice buckets at the right end and the left end that keep your value to be 0 there, then the heat or the energy in this rod would dissipate, or not dissipate, let's say flow away over the boundaries. So in the limit behavior, you would expect that our solution reaches the 0 state, or it gets the boundary conditions because we don't have any forcing. And also what we see is that the peak moves a little bit to the right. You can do a lot of analysis on that, but I will just leave that here for a thought. You could of course also play around with the parameters, and it's super interesting to see how high PETSc can go in this super simple example. So let's for instance use 1001 points, re-execute, and it's still running super fast. Let's close that and maybe go to 5000, and that's probably, yeah, it's still super fast. And I would encourage you to play around with this one here. But we could also be interested in seeing some monitoring on the linear system solve. So let me go back to 1000 here. And we can do that by adding the option -ksp.monitor. And this is basically the argument that is then parsed with the PETSc init and then set to the operator here, set from options. And what it does, let's just do it. you see it prints out the residual of our GMRes iteration. And there is a preset tolerance. I'm not sure, I think it's 10 to the minus 6 or something. And what you see here is that in the 0th iteration, so before the start of the GMRes, it has a residual that is around 5. And then within one GMRes iteration, it can reduce it to 10 to the minus 13. So it only takes one iteration to solve this linear system of equations. Of course, if you have more complicated systems, this takes more, or you might have to look into preconditioning. But for this particularly simple example, that is sufficient. And run it once again and say that this is now the end of the video. I hope you enjoyed this quick introduction to PetSc for Python and find it useful for your work. I would be happy to hear your thoughts in the comment section below for what you might have used PetSc, and also share your information there. That would be super helpful for the audience. You can find the source code file on the GitHub repo of the channel. Feel free to download it, play around, or even extend it. I would be really interested to see what you come up with. A big thanks to all the Patreons of the channel. If you also want to support my vision of free education on these advanced mathematical topics, you find the link to the Patreon page down in the video description. If you enjoyed the video, then please also consider liking and subscribing. I would extremely appreciate this. Here you will now see similar videos, and I hope to see you in the next one.